Hello my precious friends, I really hope that you are doing great. Welcome to our today's class. It's our third lesson on the 11th topic of Form 4, which is called electronics. As usual, let me commence by giving the quote of the day, which states that gratitude is the foundation of true happiness. We shall discuss that quote at the end of our class today. So today we are going to discuss what we call the PN junction diode, and we are going to start by defining it. So a PN junction diode is simply an intrinsic semiconductor doped simultaneously by both trivalent, that is group 3, and pentavalent, that is group 5 atoms, such that one half of it becomes a p-type and the other half becomes the n-type. Now, there are two ways of biasing a PN junction diode. Remember, to bias simply means to connect. Therefore, we can say that there are two ways of biasing or connecting a PN junction diode. One is what we call the forward biasing or forward connection, and two is what we call reverse biasing or reverse connection. So let's start by discussing what we mean by a forward biasing or forward connection of a PN junction. Now, a PN junction diode is said to be forward biased or forward connected when the p-type region is connected to the positive terminal of a cell or the source of power in that particular case, and the n-type region is connected to the negative terminal of the cell or the source of power. For example, you can see in this particular case, the positive terminal is connected to the p-type region and the negative terminal is connected to the n-type region. Therefore, this is an example of what we are calling the forward biasing. The p-type is connected to the positive terminal of our source of power and the n-type is connected to the negative terminal of our cell, which is the source of power in this particular case. Now, when a PN junction diode is forward biased, it allows current to flow only in one direction. That is, a forward biased PN junction allows electrical conductivity. So remember that electrical current will always flow from the positive terminal towards the negative terminal. So it will flow from the positive terminal of the cell. Then of course this one, the I represents the direction of the current. Of course the current goes through the p-type region of our PN junction, then through the n-type region, then to the negative terminal of our cell. Remember, when you connect the p-type to the positive terminal and the n-type to the negative terminal, the electrical resistance offered by this particular PN junction connected is very low, such that it allows most of the current to actually flow through the circuit. So that simply means that if you are to connect an electrical appliance, for example a bulb, on this particular circuit, then the bulb is going to light brightly, because showing that a current is being allowed to flow through this particular forward biased PN junction. Then of course this is an electrical symbol for a diode. So of course you can see this side represents the positive side of our diode. So the positive side is connected to the positive terminal of the battery, then or the cell. Then the negative terminal of the diode, so this the negative side, is also connected to the negative side of our source of power. So when a diode is connected in such a manner such that that is the P region or the positive region is connected to the positive terminal of the cell, and the negative or the N region is connected to the negative terminal of our source of power, then we say that this particular diode is actually forward biased. Therefore, it will allow current to flow only in the direction from the positive terminal through the diode to the negative terminal, but it's going to resist any current that is flowing in the opposite direction or trying to flow from the negative terminal to the positive terminal. So when it's connected this way, it allows very low electrical resistance, hence most of the current flows through. Then the characteristic for a diode in the forward bias mode is as shown in the graph. So remember, when we talk of characteristic, we simply mean the graph of current against voltage for a forward biased diode. So you can see when the voltage is 0, the current is 0. But as the voltage increases up to a certain level, what we call the cut-in voltage, the current actually increases rapidly. That is beyond the cut-in voltage. So the cut-in voltage is simply the minimum voltage for a forward biased, that is current, the minimum voltage beyond which the forward biased current actually increases rapidly. So the current increases slowly, but when it reaches at the cut-in voltage, it actually increases rapidly. That is why you can see the graph is moving at a faster rate. That is after the cut-in region. So the diode is non-ohmic, simply showing that the electrical current and of course the voltage are not directly proportional to one another, because if they were to be directly proportional, or if they were to obey the Ohm's law, then it means that the current and the voltage should be directly proportional to one another. And in that particular case, we will expect a straight line graph that is separating or at the midpoint of this particular two axes. But you can see it is a curve. It is not a straight line graph, showing that the diode is non-ohmic. That is, its current and voltage does not increase proportionately. So the current, when the voltage is increased slowly, its current also increases. But when we reach at a certain level of voltage, what we are calling the cut-in voltage, actually the current increases rapidly as compared to the voltage. Therefore, the current increases rapidly when the forward bias voltage is increased beyond what we are calling the cut-in voltage. That is the minimum voltage beyond which the forward biased current actually increases rapidly. Next, we look at the second way of biasing or connecting a PN junction diode, which is called reverse biasing or reverse connection of a PN junction diode. So, a PN junction diode is said to be reverse biased or reverse connected when the P-type region is connected to the negative terminal of a cell or the source of power, and the N-type region is connected to the positive terminal of the cell or the source of power. For example, this is a reverse biased PN junction, such that you can see that the P-type region is actually connected to the negative terminal of our cell, and the N-type region of the PN junction is actually connected to the positive terminal of our source of power, such that as the current flows from the positive terminal, actually it is going to meet the N-type region. Therefore, this particular PN junction is going to offer very high electrical resistance to the flow of this particular current. Therefore, when a PN junction diode is reverse biased, it offers very high electrical resistance to the flow of current. Hence, a reverse biased PN junction does not allow current to flow through, and therefore it does not conduct electricity. So you can see the N-type region of our diode is actually connected to the positive terminal of the cell, and that is the P-type region of our diode is also connected to the negative terminal of our cell. Therefore, this particular diode is said to be reverse biased or reverse connected, and therefore it is going to offer very high electrical resistance to the flow of current, and therefore it does not allow the current to flow through. Therefore, it does not conduct electricity. Unlike for the case of forward biasing, whereby the PN junction was actually allowing flow of electrical current. So, as reverse bias voltage is increased, there is no significant change in the current until a particular voltage, what we are calling the Zener voltage, or simply put, the breakdown voltage, when a current surge is noted. Therefore, this is the characteristic of a reverse, that is a reverse biased diode. A characteristic simply means that a graph of current against voltage. So actually, the voltage, when that is as the reverse bias voltage is increased, there is no significant change in current. You can see that the current is actually remaining constant until you reach at what we call the Zener voltage, or the breakdown voltage, when the current actually surge. That is, the current surge is actually noted. So you can see the current is actually surging at this particular point, what we are calling the breakdown voltage, or simply the Zener voltage. Then when we combine, that is a combined characteristic of a diode. That is, combined characteristic simply means that we are combining a graph for both forward biasing and reverse biasing of a diode. So this one, the right hand side, actually represents the characteristic for a forward biased diode, such that you can see that this one is representing the forward biased current. Then of course this one is representing the forward biased voltage. Of course, beyond what we are calling the cut-in voltage, actually the voltage increases with a rapid increase in current. Then on this side we are having what we call that is the reverse biased voltage. Then of course on this axis we are having what we call the reverse biased current. So you can see this is what we are calling the graph that is representing the reverse biased characteristic. Therefore, this is a graph that is combining both forward biasing of a diode and of course reverse biasing of this particular diode. Next, we look at our first example, which reads that the diagram below shows a circuit with two diodes D1 and D2, two lamps L1 and L2, and a battery. State and explain the observation that will be made when the switch S is closed. So when we close the switch S, the current is going to flow from the positive terminal of the battery through this particular path. Then when it gets to this particular point, the current will be diverted. Some of it is going to flow through the upper side. When it meets the diode D1, it finds that the diode D1 is actually forward biased, because you can see that the p-type region of the diode D1 is connected to the positive terminal of the battery, and the n-type region of our diode D1 is connected to the negative terminal of the battery. So because the diode D1 is forward biased, it will actually allow current to flow through it to the bulb L1. Then of course the current is going to flow back to the negative terminal of the battery. Therefore we expect the bulb L1 to light, because the diode D1 is forward biased, hence allows current to flow past it through L1 back to the negative terminal of the battery. Therefore, the observation expected is that the bulb L1 lights because D1 is forward biased, hence allows current to flow through it to the bulb L1. Then, for the case of the diode D2 and the bulb L2, the current is going to flow from the positive terminal of the battery. When it gets to this particular junction, some of the current will start flowing to the lower side of this particular circuit. However, when the current gets to the diode D2, it finds that the diode D2 is actually reverse biased, because the n-type region of this particular diode D2 is connected to the positive terminal of the cell, and the p-type region of the diode D2 is connected to the negative terminal of our battery. Therefore, because the bulb D2 is reverse biased, it is going to resist the flow of current through it. Hence, the bulb L2 will not receive any current. Therefore, it will not light. So, L2 does not light because the diode D2 is reverse biased. Hence, it resists the flow of electrical current through the bulb L2. That is why L2 is not going to light. Then we look at our second example, which reads that the circuit below has identical bulbs L1 and L2 and diodes D1 and D2. Explain what happens when, part A, the switch S1 is open and S2 is closed. Remember, when we close the switch S2, the direction of flow of current will be from the positive terminal of the battery through the bulb L1. Then of course, because the diode D2 is actually forward biased, because you can see that the p-type region of D2 is connected to the positive terminal of the battery, and the n-type region is actually connected to the negative terminal of the battery. So because the diode D2 is forward biased, it is going to short circuit that is the bulb L2. To short circuit simply to mean that the diode D2 is going to draw most of the current. So most of the current will flow through L1. Then when the current gets through this particular junction, because D2 is forward biased, it is going to take most of the current to the lower side. So most of the current will flow through the lower side, then of course through this particular path back to the negative terminal of the battery. So that simply means that the bulb L2 would remain with very little current because D2 is short circuiting it, or drawing much of the current through the lower side, then back to the negative terminal of the battery. Therefore, we do not expect L2 to light brightly because of the short circuiting caused by D2, which is actually forward biased. So when the switch S1 is open and S2 is closed, that is the diode D2 conducts heavily, hence short circuits the bulb L2, or it reduces the amount of current flowing through L2. Hence, only the bulb L1 lights brightly because most of the voltage drop is across the bulb L1, because remember, only little current is flowing through L2 because the diode D2 has caused a short circuiting. So because we are having most of the voltage drop at the bulb L1, that is why the bulb L1 is going to light brightly as opposed to our bulb L2. Now in part B, when the switch S1 is closed and S2 is open, so we are opening switch S2 but we are closing the switch S1, the direction of flow of current will be from the positive terminal through L1. When the current gets through this particular point, as it tries to go through that is the diode D1, it finds that D1 is actually reverse biased, because that is the n-type region of this particular D1 is connected to the positive terminal of the battery, and the n-type, that is the p-type region, is connected to the negative terminal of the battery. Therefore, the diode D1, when S1 is closed, the diode D1 will actually be reverse biased. Therefore, it will not allow current to flow through this particular path. Then remember, S2 is open, so that means current can also not flow through D2. Therefore, the only remaining direction through which the current will flow will be from the battery through L1, then through L2, then back to the negative terminal of the battery. So that means that L1 and L2 are going to share that particular current. So when the switch S1 is closed and S2 is open, the diode D1 is reverse biased. Hence, it does not take up any current. So that simply means that the bulbs L1 and L2 are both going to light, but they are going to light dimly because they are sharing the current which is flowing through the positive terminal through L1 and L2 back to the negative terminal, because the current does not flow through the diodes D1 and D2. So the diode D1 is reverse biased, hence it does not take up any current. So therefore the bulbs L1 and L2, they light dimly because they share the voltage supply. Next, we look at our third and last example, which reads that use the information given to answer the following questions. Then we are told to assume that the diodes D1 and D2 are ideal. So we are told to find part A, the total current flowing through the circuit. Now, if this is our source of power, then of course we expect current to flow from the positive terminal of the battery through the 2 ohm resistor. Then of course, as the current tries to get through the diode D1, it finds that D1 is actually reverse biased, because you can see that the n-type region is actually connected to the positive terminal of the battery. However, the diode D2 is actually forward biased, because you can see that the p-type region is actually connected to the positive terminal of the battery, and of course the n-type region is connected to the negative terminal of the battery. So D1 will not allow current to flow through because it is reverse biased. Therefore, the direction of flow of current will be from the positive terminal of the battery through the 2 ohm resistor, then directly through the diode D2, which is forward biased, then of course through the 8 ohm resistor, then of course back to the negative terminal of the battery. Now, from Ohm's law, remember Ohm's law, we did it under a given topic in Form 3, which was called current electricity 2, whereby we said that V is equals to IR. So if we want to get the total current through the circuit, then of course total voltage through the circuit must be equal to the product of current through the circuit and the resistance through the circuit. So because we are already given the total voltage through the circuit, which is 10 volts, what we just need to find is the total resistance. Now, when you look at the 2 ohm resistor and of course the 8 ohm resistor, these ones are in series connection, of course, with the battery. Therefore, total resistance in series connection is given by the sum of the individual resistance. So R total is equals to resistance through the 2 ohm resistor and the 8 ohm resistor, because those are the resistors through which the current is passing through. Remember, current is not passing through the 3 ohm resistor because it is being blocked by the diode D1, which is actually reverse biased. Therefore, total resistance is equals to 2 ohm plus 8 ohm, which is equals to 10 ohm. Now, from V is equals to IR, if I make total current subject of the formula, I'll divide through by R total. Therefore, total current is equals to total voltage divided by total resistance. Total voltage we are given as 10 volts, then divided by total resistance, of course, is 10 ohm. So if you take 10 divided by 10, you'll get 1 ampere as the total current through this particular circuit. Then in part B, Roman 1, we are told to find the voltage drop across Roman 1, the 2 ohm resistor. Now, if you look at the 2 ohm resistor, is actually in series connection with the battery. Now, if we want to get the voltage drop, V is equals to IR. So voltage drop across the 2 ohm resistor is equals to current across the 2 ohm resistor multiplied by the resistance through the 2 ohm resistor. Of course, we already have resistance, so we need to find the current. So the current through the 2 ohm resistor is equals to the total current, because the 2 ohm resistor and the battery are in series connection. Therefore, the current through the 2 ohm resistor is equals to the total current, which is equals to 1 ampere that we have computed in part A. Therefore, the voltage drop across the 2 ohm resistor is equals to IR. So the current is 1 ampere times the resistance is 2 ohm. 1 times 2, you'll get 2 volts. So this is the voltage drop across the 2 ohm resistor. Similarly, they want us to find the voltage drop across the 8 ohm resistor. V is equals to IR. The current through the 8 ohm resistor is also equal to the total current, because the 8 ohm resistor is also in series connection with the source of power. Therefore, current through 8 ohm resistor is equals to total current, which is equals to 1 ampere that we computed in part A. Therefore, voltage drop across the 8 ohm resistor is equals to IR. So the current is 1 ampere, the resistance is 8 ohm. Therefore, 1 times 8, you'll get 8 volts as the voltage drop across the 8 ohm resistor. Lastly, I have an exercise that I recommend you should try at your own free time to gauge the understanding of the concepts that you have just learned. Of course, if you have any challenges in handling any of the questions, feel free to drop a comment specifying the question that you need help in. And as usual, I'm always here to try and help where possible. So we've come to the end of our class today, but we need to discuss the quote of the day. The quote of the day stated that gratitude is the foundation of true happiness. So the quote is reminding us about the importance of being grateful for the small steps we achieve in life. Recall that a grateful mind will always attract positive thoughts, which will in turn attract great things in life. The more grateful we are, the more we attract other things to be grateful for in life. And lastly, remember that gratitude transforms common days into great days. Similarly, gratitude transforms opportunities into blessings. Thank you very much for accompanying me until the end of this particular lesson. I do not take it for granted. In case you are new to the channel, kindly hit the subscription button and also turn on the notification bell so that whenever I upload a new video, you'll get notified. Until next time, this is Kind Tuition Academy. Thank you very much.